So I want to introduce something new today. The topic that I'll introduce today will be the topic that we'll study for the rest of the semester. So this is like part 2 of this class. Now we'll start talking about trigonometry. So when I say trigonometry, how many people already have some impression of what trigonometry is? Okay. How many people would even say that they feel pretty comfortable with trigonometry? Okay, that number's a little bit higher. Well, hopefully everyone whose hand wasn't up will feel comfortable with trigonometry by the end of the semester. So let's talk through it. So here is the fundamental function that we'll study when we talk about trigonometry. Start at the point 1, 0 on the circle of radius 1. Then rotate counterclockwise about the origin an angle of theta. I'll often use Greek letters to indicate angles, thetas, alphas, betas. You'll end at some point in the plane. So you'll end at some point, x comma y. The coordinates of that point are the trig functions. Cosine theta is the x coordinate of that point. Sine theta is the y coordinate of that point. So those will be the functions that we'll study. But that's the last time today that I'll mention sine or cosine. Today I want to focus in on angles. And so, I don't know, clearly there's a sense of size to an angle. So maybe we can associate a number to it which will record how big that angle is. And let's start developing ways to do that. Let's start measuring angles. And maybe one which is intuitive just because it's one that you've seen repeatedly is degree measure of an angle. Let's talk about degree measures. So let's start by even just thinking about this. If someone mentions an angle of 1 degree, what is that angle? And let's start with this. 1 full revolution, how many degrees makes up 1 full revolution? 360. 360. And there's no reason that 360 degrees should be 1 full revolution. 1 degree just corresponds to 1/360th of a full revolution. So 1 degree is 1/360th of a full revolution. And in order to make sense of what this will then mean, let's figure out how big an angle 90 degrees is. Even though, you all in some sense already know what I'm going to draw in the picture to the right, but let's figure out why. So let's try to convert 90 degrees into full revolutions. So 90 degrees, well, that should be 90 degrees times 1 full revolution per 360 degrees. So the units of degrees will wind up canceling, and that'll be 90 over 360 of a full revolution. But what is 90 over 360? It's a quarter. All right, and how would you see that? Well, I guess one way would be you can throw out the extra zeros, right? That's 9 times 10 in the top and 36 times 10 in the bottom. So you really have 9 over 36. And, well, you recognize 36 as 9 times 4. So a 90-degree angle is 1/4 of a full revolution. So that's that big an angle. That seems right. And that's what you already knew I was going to draw. A 90-degree angle is a right angle. So I'll try to, for the most part, avoid walking in degrees most of the time in free calculus, because there's nothing natural about degrees. There's no reason to take a circle and break it up into 360 evenly sized pieces. That's an arbitrary choice. The only reason we did it is because the Babylonians did it, and the Babylonians did it because they kind of walked in a base 6 number system. So that's a bit of history, but that kind of means that there's no reason to have made the choice of walking in degrees. I'll try to come up with a totally natural measure of angles. And here's how I'll do it. So here's the radian measure of an angle. So stand on a circle of radius r. Let's even draw a picture. There's a circle. That is a perfect circle. I won't have anyone tell me otherwise. Yeah. So now you understand the joke about how I'm claiming that that's a perfectly drawn circle. Of some radius r. So the distance from the midpoint to any point on the circle is r. If you stand on the edge of this circle and walk some distance s, how about that distance? So walk counterclockwise around that circle some arc length s. So that's now like totally geometric. I've just measured the length that I've walked on the edge of the circle. Well, that's traced out some angle, theta. The radian measure of that angle, so if you stand on a circle of radius r and walk counterclockwise until you've covered a distance of s, you have now traced out an angle of s divided by r radians. Theta equals s divided by r. So notice, in order to do that, I just need to know how to measure a distance. And let's even check this out. So if I measure the radius in feet, and I measure the arc length in feet, then what does it look like the units on that angle are? Well, feet divided by feet, so it's unitless. There are no units. So really, 1 radian is like a ratio. When you give the radian measure of an angle, you say if you draw any circle and you draw that angle inside of that circle, that angle, theta, is the ratio of arc length over radius. That makes sense? So let's do some computations then. Here are some pictures. All right, here I have drawn an arc length of 2 centimeters on a circle of radius 2 centimeters. What is the radian measure of that angle? 1. Because that should be theta equals s over r. So that'll be 2 centimeters, because s is 2 centimeters, divided by 2 centimeters. That's 1. And I'll stick the radian there just to really emphasize that I don't mean 1 degree, I mean 1 radian. Here is an arc length of 6 centimeters drawn on a circle of radius 1.5 centimeters. What's the radian measure of that angle?
4.
4, I think? Yeah. Theta is 6 centimeters divided by 1.5 centimeters. So I mean, I guess if you want to like do the division algorithm, you would write it as 60 over 15, which is 4 radians. That seems okay? Nice. So on the one hand, so I guess degrees are nice in the sense that I can talk about an angle of like 45 degrees, and you know what angle I mean, but the only reason you already know what angle I mean is because you've been told what a 45-degree angle is when you were like 2 years old. Radian measure has the naturality that, the advantage of that it's totally natural. You measure a distance, you measure another distance, you take a ratio, that's the radian measure. So there's not this arbitrary choice. But if we have 2 different ways of measuring angles, we should be able to convert from one to the other. So let's try to convert from one to the other, and let's do it by passing through how many radians or degrees it takes to make a full revolution. So let's figure it out. So let's figure out what angle corresponds to a full revolution by talking through what the definition of a radian measure is. So let's start at a point on the unit circle. Let's walk counterclockwise all the way around the circle. So start at a point on the circle, walk all the way around the circle. So the length of the arc you just walked is the circumference of the circle. What's the formula for the circumference of the circle of radius r? Yeah, but say it louder. Almost 2 pi times that. So where r is the radius of the circle? Is that enough information to figure out the radian measure of this angle? Yeah, it should be s divided by r. So it should be 2 pi r, because that's s divided by r, because that's the radius, or 2 pi radians. Well, maybe I should just disclose this. So you're noticing that when I say the letter R, it doesn't sound like the letter R. That's just a speech thing that I have. I went through several years of speech therapy in my distant childhood, and I never quite figured out the letter R. So you'll just have to put up with that. My R sounds like it might be an L. Wait, so let's see what we just did. So one revolution makes up an angle of how many radians? 2 pi. Nice. So, well, I guess kind of we have 3 measures of angles now. We have how much of a full revolution is it? How many radians is that angle? How many degrees is that angle? And you know how to convert from degrees to radians, because 1 degree is 1/360th of a full revolution. You know how to convert from full revolutions to radians, because 1 full revolution is 2 pi radians. So we should be able to convert all the way from degrees down to radians. Let's do it. And right, it'll just be like the standard trick for you doing unit conversions. Divide by 1 in an appropriate way. So let's try to take an angle of d degrees and convert it to radians. And I guess this is it. So 1 full revolution we just found is 2 pi radians. How many degrees is a full revolution? 360. 360. So 360 degrees is 2 pi radians. So let's use that fact. So if I want to convert d degrees into radians, well, first I'll multiply by 1. How many? So 360 degrees is the same as 1 full revolution. So 1 full revolution times 360 degrees divided by 360 degrees, that's 1. A thing divided by something that's equal to that thing is 1. So I can multiply by 1 and not change anything. And notice, if I do that, then the degrees will cancel. They appear in the numerator and the denominator. And I'll have converted to full revolutions. How many radians does it take to make a full revolution? 2 pi. So that means 2 pi radians divided by 1 full revolution is also 1. So I can cancel those units again. And I see that d degrees times 1 over 360 times 2 pi over 1 gives us the radian measure of the angle. So d degrees is the same thing as d times 2 pi over 360 radians. So if you want to convert from degrees to radians, multiply by 2 pi over 360. But if I plan on actually using this formula repeatedly, should I simplify the thing on the right-hand side? You know, what does 2 pi divided by 360 simplify to? Pi over 180. Right, there's a 2 in the numerator and in the denominator. So d degrees is the same thing as d times pi over 180 radians. That makes sense? Well, So if we can convert from degrees to radians, presumably we can just do the opposite to convert from radians to degrees. If I give you an angle of theta radians, that'll be the same as theta radians times 1 revolution divided by 2 pi radians times 360 degrees per 1 full revolution. The units now cancel. Radians divide by radians. Revolutions, but then I divide by revolutions. So I get theta times 360 over 2 pi degrees. And again, there's a simplification, right? 360 is even, and there's a 2 in the denominator. So that's the same thing as theta multiplied by 180 divided by pi degrees. That makes sense? So now you have 3 different ways of measuring angles. Different ones are suitable for different purposes. If you're doing something that involves abstract mathematics, chances are you want to be using radians. Radians are the one that actually has a concrete mathematical definition. If you're thinking about something in terms of full revolutions, so you want to compute how many revolutions per minute something is going around, maybe you want to be working on full revolutions then. If you have an application where someone's given you a measure of an angle in, say, the real world, it's nice that the degree measure of an angle that you're likely to encounter is probably somewhere between 0 and 90, a reasonable number to work with. So that's why often degrees are used if you're taking measures of, say, angles of elevation from the ground to the top of a building. Nice. But they're all the same, right? You know how to convert between them. So let's do some conversions. A 30-degree angle, how many radians does that make? And we know exactly what we need to do. That'll be 30 degrees is the same thing as 30 degrees times pi radians per 180 degrees. So that's 30 times pi divided by 180 radians. All right, that simplifies. Like at the minimum, both the numerator and denominator shouldn't have a 0 at the end. So it's really 3 pi over 18 radians. Is 18 a multiple of 3? Yeah, 18 is what? 3 times 6? So that's really 1/6. It's pi over 6 radians. I think that I want to be quiet for just a little bit, and I want you guys to compute for me the measure of an angle, which is the degree measure of an angle that is pi over 5 radians. So do that really quickly. Maybe even take a second and compare with those around you. So what is that degree measure?
36 degrees.
Do we have any differing answers? Because I feel like I got a different answer than I did. Let's make the conversion really quickly. Oh no, that's fine. That's right. That's 36. I was thinking 2 pi over 5. Yeah. 36 degrees. So let's also, right angles are important, so let's figure out the radian measure of a right angle. So a right angle we've already seen is 90 degrees. Let's figure out its radian measure. So if you want the radian measure, you know what to do. That'll be 90 degrees times pi radians per 180 degrees, which is how much? well, I guess it'll be 90 times pi over 180 radians, which simplifies to pi over 2. 180 is 2 times 90. So pi over 2 radians is a right angle. And that's an important number that's worth remembering, how big a right angle is in a radian measure. Cool. So now that we have some of the ideas of how you measure angles, I want to get a few geometric formulas. So far we've talked about if you draw a circle, again, that is a perfect circle, and I tell you the radian measure of an angle theta, then you know that if this is S and this is R, then S over R equals theta. Does that mean that, does that look like a formula that you could maybe solve for S? Yeah, so one automatic fact that you know, S is equal to R times theta. If you know the radius and the angle you trace out, you know the arc length. But here's another thing you might ask. How much area is in that slice? And let's try figuring it out first by drawing an explicit picture. Suppose you have a blueberry pie. You can replace that blueberry with a different type of pie if you prefer, of radius r. And you cut out a single piece which corresponds to an angle of pi over 4 radians. So let's draw a picture. So here is the pie. I'll draw an angle of pi over 4 radians. And I'll ask how much area is in that slice. And here's how I'll figure it out. What's the formula for the area of a circle of radius r? Pi r squared. Pi r squared. So the area of this whole pie is given by pi times the radius squared. And how many radians are in a full circle? 2 pi. So that means if I cut out an angle of 2 pi radians, I would have just cut out the whole pie. So the area that would correspond to 2 pi would just be pi r squared. Well, let's figure out how many times pi over 4 goes into 2 pi. So the number of slices is, let's see, There, okay, this question. How many times does this piece of pie fit into the whole thing? So let's answer this question. I didn't give myself enough space. So that'll be, how many times does pi over 4 go into 2 pi? So that's 2 pi divided by pi over 4. That is what you mean when you say, how many times does this go into that? You mean do some division? Well, let's see. By looking at that, that's like a fraction in the denominator. So that's 2 pi times 4 over pi. And what does that equal to? 8. 8. So this slice makes up 1/8 of the whole pie. So the area of that single slice should be the area of the whole pie, pi r squared divided by 8. Now, of course, there was no reason for me to focus on this particular angle, right? I could have done that for any starting angle. So let's do it for any starting angle. So let's suppose you have a circle of radius r. There's a circle, radius r. You trace out some angle, theta, measured in radians. Let's figure out how much area is in this sector. Now, just as before, a full circle contains 2 pi radians. And this is an angle of theta radians. So that means, well, how many times does this particular slice go into the full circle? Well, that'll be 2 pi divided by theta times. And you still know the area of the full circle. That's pi r squared. That formula hasn't changed. So if you want to find the sector area, well, that's the area of the whole circle, pi r squared, divided by 2 pi over theta. By just putting together the ingredients that we already have. So on the one hand, that gives us a formula. The area of a sector is pi r squared divided by 2 pi divided by theta. But that's like a needlessly complicated formula right now. It simplifies. So that will be the same thing as pi r squared dividing by a fraction divided by pi multiplied by theta. Does anything cancel? The pi's cancel. That's good. Leaving me with r squared theta I lost the 2, divided by 2. So here's the theorem. If you start with the circle of radius r, and you draw in that circle a sector of angle theta, where what is a sector? A sector is, well, something that looks like that. Of angle theta, then the area of that sector is, for emphasis, I'll write sector area, is equal to r squared theta divided by 2. And let's notice, that was, yeah.
So theta will always be in radians. So.
If you want to use this formula, theta has to be in radians. You could get a formula in degrees by doing the same analysis. You would, I guess, replace the 2 pi's by 3/60s. And the formula you would get would be like the same formula as this, but it would differ from it by a factor of, I guess it has to be 180 over pi or pi over 180. But that formula will be just uglier. Which is the reason to walk in radians. All of the formulas will be nicer looking if you walk in radians. So you could get such a formula in degrees, but I won't, and I don't think you should. Instead, if you have a situation where you want the area of a sector in degrees, just convert degrees to radians. And in fact, let's do exactly that. So let's start with this item 2, because that's more appropriate for the question just asked. Let's suppose you have an angle of 1 degree inside of a circle of the radius 20. Let's compute the area in that sector. So I have this formula. Area is r squared theta over 2, but that only works if theta is in radians. So first let's convert 1 degree into radians. So 1 degree. What do I need to multiply by to convert from degrees to radians? Pi over 180, because pi radians is the same thing as 180 degrees.
Move it up a little, please.
Yes. So 1 degree is the same thing as 1 degree times pi radians divided by 180 degrees, because this quantity, pi over 180 degrees, is exactly 1. So this is the same as pi over 180 radians. Has that successfully converted the degree measured angle to a radian measured angle? So now we can use the formula. Area is r squared theta over 2 equals, what's the radius in this problem? Well, that's theta. That's relevant, though. Pi over 180. But what's the radius? 20. So it'll be 20 squared times pi over 180, all that over 2. And in some sense, there's an answer. Does it look like it probably is an answer that could have some simplification done to it? Totally. So that'll be, let's see, we can rewrite it as a single fraction, right? That 180 just belongs in the denominator. So that'll be 400, because that's 20 squared, times pi divided by 180 multiplied by 2. That bit of fraction manipulation seems okay?
let's simplify. So certainly, I noticed that.
The numerator is a multiple of 10. The denominator is a multiple of 10. Take a multiple of 10 out of both sides. What other simplifications do you see? Is the numerator a multiple of 2? Is the denominator a multiple of 2? So
You can get rid of this 2 at a cost of taking a 2 out of the 40. So that brings me down to 20 pi over 18.
And let's just keep on simplifying. Is that numerator still even? Is the denominator still even? So you can do it again. (10 pi over 9). Is there any other just cancellation you see that you can do? And I don't know, maybe you care about the bigness of the number. So let's get a decimal approximation too. What is 10 times pi over 9? I'm going to go ahead and say that it's like 3-ish. And what's my justification there? 10 is pretty close to 9, so 10 over 9 should be pretty close to 1, and then pi is pretty close to 3. So 3-ish. But what is it exactly? 3.49.
It's approximately 3.49.
Were we given any units on the radius? I think it was just said to be radius 9. So we can't put any units in. The area is just 9.
Whatever units we were walking in would be squared. People feel pretty good about that formula? Good. So the next thing that I want to talk about is
Let's talk about spinning gears, or wheels. If you have some gear or wheel that's spinning, you can talk about 2 different measures of velocity. You can say, well, how many radians is this thing tracing out per second, or degrees, or full revolutions? That's the angular velocity. You can also say, well, if I had a point at the edge of the gear, how fast is that point moving? That's the linear velocity.
So the angular speed in rotation, often measured in radians per second, is just given by how large an angle is traced out in any given fixed time period. That seems like a reasonable definition, right? The linear speed is just how much distance does a point at the edge, maybe I should divide by time. How much distance does a point at the edge of the wheel circle cover in some fixed time, divided by how much time passed. That seems like a good definition for linear speed and angular speed. Linear speed is literally how fast is a point at the edge of the gear moving. Angular speed is how big a degree are you tracing out. Do those seem like they should be related somehow? Right, if you have a gear that's tracing out an angle very slowly, a point at the edge of the gear is probably traveling correspondingly slowly. Let's get a relationship. So let's suppose you have a gear of radius 1 thought feet. It spins 2 radians every second. Let's find its linear speed. So what am I going to do? I'm going to do it in this particular case, and then I'm going to write down a general formula. So let's figure it out by thinking about, in 1 second, what happens. So if you have a gear of radius 1 thought feet spinning at 2 radians per second, let's let that spin for 1 full second. How many radians get traced out in that 1 full second? 2, because it's going 2 radians every second. If you wait 1 second, you get 2 radians. So I guess that's the thing that we've been calling theta. That's the angle traced out. Can we use this to figure out how big an arc is traced out by this point on the edge of the gear? Yeah. S is equal to r times theta, where what's the radius of this gear? 1/3 feet times the radian measure, or 2. So that's 2/3 of a foot. So let's think about that. That means that in 1 second, a point on the edge of the gear travels 2/3 of a foot. Is that enough information to determine the linear speed? How much distance does the point cover? 2/3 of a foot. I guess that's the same as 8 inches, but let's stay in feet. Is that 8 inches? Yeah, that's 8 inches. How much time did we allow to pass? 1 second. So distance, 2/3 feet divided by 1 second. The linear speed is 2/3 of a foot per second. Nice. That seemed pretty okay? We could do this for any choice of theta and any radius and any speed. So here's a formula. The linear and angular speed are related by the following formula. V is equal to r times omega, where, let's remind you, v is the linear speed, omega is the angular speed. And for emphasis, that omega is measured in radians per unit time. Do you think you could do this also in degrees? Yeah, of course you could. But you would get an uglier formula. You would get a formula that differs from this formula by like pi over 180 or 180 over pi. And I think I have time to do one example. So I'll encourage you over the weekend, think about the things in the remainder of these notes. I won't go over them unless someone asks me a question about them. If someone does, then I'll happily spend time on them. If you have a gear of radius 5 inches, let's suppose it's spinning 6 revolutions per minute. Let's compute its linear speed. Well, let's see. Do I know the radius of this circle? Yeah, it's 5 inches. Do I know the angular velocity of this gear? Yeah, it's 6 revolutions per minute. Is that in radians yet? No, but it's easy to convert, right? How many radians is a full revolution? 2 pi. So that means 6 revolutions per minute should be 6 times 2 pi radians per minute, also known as 12 pi radians per minute. Now, do I know so I still know the radius. Do I now know the angular velocity in radians per minute? So v is now 5 inches. It's r times omega, 12 pi per minute. Right, radians in some sense have a unitless quantity. So if you take radians and you multiply them by a unit, that other unit just takes over, resulting in 60 pi inches per minute. That seem reasonable? And you could get a decimal approximation now if you wanted to. I think that I don't want to. So what's in the remainder of this document? So there's another example of just computing angular speed. There's another example in which if you have 2 gears connected to each other so they mesh, then both of those gears have the same linear speed. points at the edge of the gear will be traveling at the same speed. You can use that to convert one of their angular velocities to the other angular velocity. And finally, if you have a car that's driving, then the speed of the car is the same as the linear velocity of the wheel on the car. So you can use that to figure out from the speed of a car how many revolutions per minute that wheel is going. So go through those last computations. We can talk about any of them that you want to on Monday. And if you check out the webpage, you will see the following. There is a video posted that corresponds to the stuff in the notes from Tuesday that we didn't do. You will see a comment saying you should go through those examples because they'll show up on quizzes and stuff. But I think that's it. I'm happy. And I guess if anyone wants to, thank you. If anyone wants to like pawn in those bonus homework problems, they can do that right now.
You said like with that case, yeah, just turn it in again after it's been graded.
If I remember that you did what you did, then when the grader gets it back to me, I'll open up after the points then, but I wouldn't count on you on that.
Okay, that's okay.
Cool.
All right, have a good weekend.
Yeah. These are the bonus things. Great. Can you wiggle them?
Yep.
Fantastic. How do you feel?
Easier than some of the other stuff we've covered.
Yeah. The content wasn't that hard, but I just didn't actually hit the stuff with it. So
Yeah.
I'll figure out what sort of bonus credit. Oh,
Okay.
That far ahead yet.
Last question, so we turned in after.
Yeah. Check the webpage maybe sometime over the weekend. I'll post a deadline. I'm going to say don't call them in at the same time as something else is being turned in. Because then I'll lose them in the shuffle. So not Wednesday. They can't be collected Wednesday. Thank you. You too.